Hello, everybody. Welcome to your lecture number 7 in Igneous Rocks. We're moving on to rocks now. We've gone through minerals and matter. Now you know that it's the atoms that make the minerals. It's the minerals that make the rocks. And we're starting with our first lecture on rocks with igneous rocks. We'll go on later through sedimentary rocks and metamorphic rocks and all that good stuff. But we are going through igneous rocks today. And I always start off with this first image of a bus that has been trapped in basalt, igneous rock. And I actually showed this picture one time to a student. They came up with a really funny thing. I was going to pop that up on there. It just said last ride of Miss Frizzle. So anyway, I thought that was a little morbid joke for you. But it's funny because I actually had this excerpt from Miss Frizzle in the Magic School Bus talking about this igneous rocks and how the earth melts. And it's a common, I hate Miss Frizzle in some ways because she perpetuates a lot of common misconceptions. But it says here the earth's crust is so hot it's melting. And we're actually going to see in this lecture and subsequent lectures that earth doesn't really melt because it is so hot. It actually melts mostly, about 80% of the melting is actually done because of low pressure. It's actually pressure changes that create the melting, not temperature changes, as you might expect. So I know that's a really weird way to, you usually don't think of things melting because of pressure, but they do melt because of pressure. That's actually the main way that Earth melts. So really it should say not that Earth is so hot, its crust is melting. It should say that the pressure is so low, the Earth's crust is melting. So, we have really low pressure here at the surface compared to inside the Earth, and that makes a big effect on the rocks. Anyway, we'll get into that later. But I hope you have your lecture assignment number 7 out. I got mine out. We're going to be going through the questions in there. So, as you know, all rocks, they are made out of minerals. That's the constitutive element of rocks. They are made of minerals. Minerals are made of atoms. You remember that minerals have this very highly ordered structure to their atoms, right? So rocks, number one, starts off, says rocks are made out of what kind of a molecule, okay? Well, I hope you remember this very famous molecule we talked about, the silicate molecule, which consists of silicon atom that is bound up together, surrounded by 4 oxygens, and it actually makes this kind of like a pyramid structure here. So you can see that pyramid, like it, and actually, it is not a pyramid. It's actually distinct from a pyramid. A pyramid has really 5 faces to it, right? That would be like I'm trying to draw 3-dimensionally. It's not working out very well. But if you think about it, like a pyramid, like in ancient Egypt, has 5 different faces to it, right? But a silicate tetrahedron, tetra means 4. It actually has 4 faces. Okay, so it's a little bit different. But anyway, we're going to see later in this lecture, in the next lecture in Igneous Rocks number 2, we're going to see how these silicate molecules all link up. You actually already saw it in the minerals lecture. And it creates a lot of interesting properties to our rocks. A lot of the properties of these different igneous rocks come from how the silicate molecules link up with each other, or if they do at all. Okay, so anyway, silicates, those are really the basic building blocks of the Earth. You might remember that Earth's crust is 75% really oxygen and silicon. Together, oxygen and silicon make up like 75% of the Earth's crust. So that obviously, look at silicate right there. It's up on your screen. It is literally like just that perfect proportion of oxygen to silicon. It's about 70, together, makes up most of the Earth's crust by weight. And most of the rocks that you pick up, if you go pick up a rock, just random rock outside, probably most of the weight of that rock is actually going to be oxygen. And another good chunk of it's going to be silicon. Okay, so most of those rocks are going to be silicate molecules. Remember that the silicate molecules, they link up in different ways. They give us these different kinds of minerals. Okay, so remember these really important 6 rock-forming minerals. You got to remember these 6, right? So starting with quartz, then feldspar. We have potassium feldspar versus plagioclase feldspar. You got to know the difference between those for the test. We have the micas, okay, that biotite mica and muscovite mica. Muscovite's shown up there on the screen. We have amphibole. We have pyroxene, and then finally we have olivine. Okay, so those are actually shown in a very specific order. It's showing you from most interconnected with quartz to least interconnected with olivine, where you actually see that in olivine, none of the silicate tetrahedrons are touching each other, whereas in quartz, all of them are all interconnected. Okay, so and it creates very different physical properties for those minerals and therefore for the rocks. So rocks are made of these minerals. Okay, granite is just made out of feldspar, quartz, and mica, for instance, and it could be feldspar, quartz, and amphibole as well, but usually it's feldspar, quartz, and mica. Gabbro, another common type of rock, but one probably you haven't heard of before, is made out of mostly plagioclase and pyroxene. You can literally, I hope you can literally see those different crystals in there. Like you can see the white crystals of plagioclase and the black crystals of the pyroxene in there, right? So we have three different kinds of rocks, all right? Igneous, sedimentary, metamorphic. That's a question on the test, basic question. Make sure you know that. In igneous rocks, what we're studying now, or in the next lecture too, we're going to be studying igneous rocks. What makes an igneous rock? They are rocks that solidify from a melt. And notice here that I say solidify, I don't say cool. You see, that's again a kind of a common misconception. Sometimes I slip up and say cool too, but it's not necessarily a melt that is cooled from a magma or a lava, okay? Because we should say crystallized or solidified. Why? Because there are different ways of causing solidification without cooling, okay? You can have pressure changes. You can have changes to with something called oxygen fugacity. You don't need to know about that, but that's a more advanced concept. But you can have solidification that comes from, but let's just say this, you can have solidification that comes from changes to the chemical concentration or the chemical makeup, okay? So there are different things that can cause that solidification besides just cooling, okay? But anyway, suffice to say, we have igneous rocks, and they are formed from the solidification of a melt. We have to start off either partially or fully with a liquid rock, okay? Rock in its liquid state. By the way, we have two kinds of liquid rock. We have lava, which has been erupted onto the surface, and we have magma, which is liquid rock that has never reached the surface. It has stayed below, okay? Now, I want you to think about this a little bit. If we have a liquid rock, magma, underneath the surface versus one that gets erupted on top, I'll just ask you, which one do you think is going to solidify more quickly? What do you think? What's going to solidify more quickly? If you think it's a lava, you'd be correct. Okay, so lava, of course, gets erupted, it gets extruded onto the surface, and that's going to be exposed to the air, and that's going to create very rapid cooling, very rapid solidification. On the other hand, you have a magma. It's going to stay underneath the ground. It's going to be insulated there. It's going to be kept at a certain pressure and a certain temperature. It's going to take a lot longer for that thing to cool down or to solidify. So this is what I want you to realize. This is going to have more time. So this one is going to have more time to solidify. This one's going to have no time to solidify. Okay, no time. I'm sorry for these little spiky things. I've been trying to get rid of these spiky things that pop out of my PowerPoints for years. It never seems to work. Somebody says I have to wear gloves when I do this. I don't know if that's true, but I ought to try it someday. I guess they do sell on Amazon little gloves for when you're doing these things. I guess don't make contact with your board, but it doesn't matter. So what defines an igneous rock? We covered that. What's the difference between a lava and a magma? We've covered that. And I want you to, put there for number 4, just put a little note. Lava's going to have no time to solidify. Magma's going to have a long time to solidify. Why is that important? Well, that's how we're going to distinguish. It's going to create a different, what we call texture. So we classify igneous rocks on the basis of texture and composition. All right. Now, a lot of people, when they hear that word texture, this is often how I know if someone's really been listening to the lecture versus looking something up on Google. What is texture in the context of geology, right? It doesn't refer to something being rough or smooth, okay? I know that's kind of our normal everyday use of the word rough and smooth. We call it texture, but I don't mean that at all in geology. What we actually, I'm going to put a big X through that, so forget about that. What do I really mean? Let me give you an example. I'm talking about, in texture, we're talking about the distribution of different grain sizes. So let me give you a little, I'm going to get my rock bowl out here. Okay, and let me give you an example of that. So, what rocks I have here. All right. Let me give you an example. Oh, I'm dropping rocks everywhere. Okay. I'm back. Okay, so, I'll just pop myself up. I'm going to make myself big. There we go. Okay, I'm big now. So, if you take a look at this is a granite. And I have to kind of get the light, because it's too shiny. There we go. That's better light. I want you to notice. Take a look at this. I want you to notice how, if you can actually see the individual grains here. Okay, so take a look, and I want you to see how you can see. The black, the pinks, the whites, the grays. You could see individual grains within this rock. Those are all the different crystals, and you can notice that the crystals in this granite are large enough to actually visibly see with the naked eye. Okay, now compare that to this. So that's a granite. I'm gonna put up basalt now. You want to take a look at the basalt. Now you notice that with the basalt, you notice it looks different, right? You don't see, it basically looks plain and black and all kind of the same. So you can't see the individual crystals in this basalt. You can see it in the in the granite. So again, you can even see up here on the screen. This is like a granite, and you can see the different the different colors, the different crystals. You can see the micas. You can see the plagioclase crystals. You can see the quartz crystals. And you can actually see it with the naked eye. That's a different texture than something like this. You notice in this one, you can't really see the individual crystals, okay? We say that they have different textures because we have different distributions of crystal sizes, okay? Sometimes you can have a mix, too, okay? Like, for example, let me show you this one with the camera. This is an andesite, okay? This is an andesite. It's really common. It's a rock from the Andes Mountains. I want you to notice how, while most of the rock is just kind of plain and black, I hope you can kind of notice there's little sparkles in there. There's some actually big crystals of amphibole in there. Okay, so you have a mix of big crystals. Maybe you can't really see it with my crummy little camera, but you have a mix of big crystals and little crystals all kind of mixed together. Okay, that's a different texture. We actually call that a porphyritic texture. So anyway, the main idea here, though, is that when we say texture in geology, we're talking about not if it's rough or smooth, we're talking about the distribution of different kinds of grain sizes in the rock. Okay, well, what causes those different grain sizes? Well, remember that a volcano, when it erupts a lava on the surface, it doesn't have very much time to solidify. It's basically just going to solidify like, boom, like that. Maybe it takes a year. Oh, wow. Well, for us, a year feels a long time, but for a volcano, a year is nothing, right? In geological time, a year is just instantaneous. But a magma solidifying under the ground, it might take 1,000,000 years to solidify. Okay, so it has 1,000,000 years to grow crystals. Now, crystals grow slowly. Crystals grow slowly. And that's because you remember how minerals are. A place for every atom, an atom for every place. It's going to take time, just like it takes time to clean your room, clean your house, and put all the things back away where they go. It takes time to put atoms where they need to go. It takes time to build crystals, to make big crystals. Therefore, you're going to end up with magmas. When they solidify, you're going to end up with this. Okay, you're going to end up with big crystals. Okay, a different texture. We call that a coarse-grained texture. Versus a lava that solidifies very quickly, you're going to end up with this basalt like this, where the crystals are there, but they're all just really, really small. Sometimes some crystals start to solidify. You know, like this andesite, it has a couple wee big crystals, but mostly it's a fine-grained ground mass. That's a volcanic rock as well. But anyway, it's all about time and how much time that rock had to solidify. Okay, so for a basalt, we would call it a basaltic texture. We would call it fine-grained. Sometimes we use another term called aphanitic. I'm going to write that down. Aphanitic. Okay, it means the same thing. It means fine-grained. Okay, it means you can't see the crystals with the naked eye. They're just too small. Versus coarse-grained, that means the crystals are macroscopic. You can see them with your naked eye. They are, now we are going to use another term here, phaneritic. Okay, phan, this P-H-A-N, comes from the Greek term visible. So aphanitic means not visible with the naked eye. Phaneritic means visible with the naked eye. Okay, so that's the origin of that word. So now another important term that you should know, okay, is this term extrusive versus intrusive. So a volcanic rock that crystallizes from a lava is extrusive. That means that it extruded onto the surface. Versus a rock that's solidified underground from a magma, we call that intrusive or plutonic. Now, those of you maybe have read about Greek mythology or something like that, or Roman mythology, you might remember that Pluto is equivalent of Hades. And that's, in Greek and Roman mythology, that's the god of the underworld. So we call that plutonic, which means, formed underground. Versus volcanic, you also might know that that's another Greek mythology term, right? Vulcan, in Greek, Hephaestus, is the god of the fire and the forge. So that's where those two different words come from, volcanic versus plutonic, okay? Now, plutonic rocks are going to have a coarse-grained phaneritic texture. An extrusive volcanic rock, on the other hand, is going to have a fine-grained texture, or maybe a porphyritic texture. We'll talk more about that in a sec. So how are you going to tell the difference between a volcanic rock and an igneous rock? Let's say you pick up a rock. How do you know if it's volcanic or if it's plutonic? Well, you're going to look at the texture, right? You're going to look at the texture. If it has those big crystals, you're going to know that it's intrusive, plutonic, magmatic. Those are all kind of equivalent terms in geology. Versus if it has real small crystals, then you're going to say that it's fine-grained. It's another term you can use is aphanitic. And we know, therefore, that this was an extrusive volcanic rock, right? That's how you tell the difference, okay? So, some other terms. Let me show you some other terms. Now, what's kind of interesting, all these other terms, these are all different textural terms that are all, they're all volcanic rocks. These are all volcanic rocks, okay? So the only kind of texture exhibited by an intrusive rock that formed inside of the earth, the only kind of texture you're going to get with that is a phaneritic coarse-grained texture. All the rest of these textural terms that you see up in front of you, these are all textures associated with volcanic rocks. First is porphyritic. So I showed you that before with my andesite. Okay, I don't know if you can really see this up on the screen, you know, but my andesite has little crystals. You can maybe see them flashing in the light. Maybe if I shine the light right on it, you can actually see the little crystals flashing. Yeah, you can a little bit. Can you see that? You can see the little crystals flashing in there. So this has mostly a fine-grained ground mass, but it has some big fat crystals that are visible with the naked eye. And those, we call that mixture of the two, fine-grained and coarse-grained, we call that porphyritic. I don't really know what the Greek root of that is, but it's definitely a Greek root. But anyway, we call that a porphyritic texture. It's a volcanic texture, common volcanic texture. Another common volcanic texture, you know, you have it up on the screen. Oh, and I have a big piece of this right here. This is kind of heavy. I could actually, I like this one. I'll show you. I don't know why that people, when they see this, they say, oh, this looks like a moon rock or something. I don't know why. I don't know why people think that looks like a moon rock, but everybody thinks of it as a moon rock. But of course, moon rocks don't actually look like this at all. But this is a vesicular basalt, a vesicular texture. And you notice it has lots of vesicles. It has lots of holes. Now, it's kind of funny, like I said, people call this a moon rock because, you know, the holes are created by gases, you know, and air trapped inside the lava that are escaping during the volcanic eruption. And, you know, the moon doesn't have any gases or air, right? It doesn't have an atmosphere. So that doesn't really happen. But anyway, that's a vesicular rock. It's a volcanic extrusive texture. Okay. Next one is one that probably you've seen before. I have a picture of it up here on the screen, but I also have a nice hunk of it right here, a really cool hunk. I always kind of wish my online students could come at least just for a day and actually hold and check out some real rocks. Maybe I should arrange something like that. But this is obsidian, right? So this is the stuff that Native Americans and all sorts of different kinds of people used to make their arrowheads and spearheads and tools out of. And I really shouldn't say Native Americans because, you know, Paleolithic people of all sorts from everywhere, all over the world, use this rock to make blades. And actually, by the way, we still do use obsidian to make blades. Even in the modern era, you can actually make an obsidian blade. This material will actually make a blade that is sharper and harder than steel, you see. So if you want something like, for example, for surgeries, and you want a super sharp scalpel, they actually use obsidian still in this day to make obsidian scalpel blades. You actually get it sharper than metal. Okay, what else do I have here? Another one, I know that you've seen this. You've probably seen this since you were in grade school. Then I'll show you again. Why not? But another one that you're going to get are porphyritic textures. I have a little movie here. You probably can't hear it very well, but I want to show you just the video. So he's talking. So he's showing you these different videos up here. I don't know if you can really hear him very well. He's probably too quiet. But he's showing you kind of what typically you think of when you think of a lava. Maybe I should just turn the volume off. Well, I don't see the volume. Do you see the volume? I don't see the volume. It's okay. But anyway, I also want to show you another one, pyroclastic textures. Okay. Now this is kind of an interesting texture. This is when you have these hot ash flows. Let me show you some of these ash flows. You know, we still have active volcanoes, of course, in Mount Etna. Let me show you. This is Mount Etna. Right, and Mount Etna is active volcano in Italy and Sicily, and it creates these explosive eruptions. The ash starts rushing down the sides of the mountain, and those ash flows will pick up other kinds of rocks and pebbles and whatever isn't there, and it'll actually integrate it into its structure, so that you get this almost looks like natural concrete, right? So that's what's called a pyroclastic. Kind of eruption. I also want to show you this because a lot of you probably seen this since grade school, and it's kind of cute. But, sometimes you can get all these gases exuding out of an erupted lava. And just like when you pour a beer, or I guess beer, soda doesn't really do this, but a beer, you know that on the beer, you get like a head, right? So you get like a thick foamy head. The same thing happens, that's that beer foam, right? It's the same thing happens with a lava, right? You get those gases exuding out. There's all these gases that are captured under the high pressure in the magma chamber, but then it gets released when it comes to the surface, and it creates a head on top of the lava, literally like a foam rock layer, and it creates this stuff, is pumice. So, and famously, pumice is so light, it actually floats on water. So there you go. There's your pumice floating in the water. And it's really just rock foam. It has a really unique texture because all of those gases get trapped in the very viscous liquid rock. Okay, liquid rock is very viscous compared to water and things like that. So anyway, thanks for humoring me with that, and let's move on. So we talked about texture now. That's all done. Okay, we classify igneous rocks on the basis of texture, and the other thing is composition. So let's move on and talk about composition. So composition refers to the different elements from the periodic table that are contained in different igneous rocks. So you can have a rock that has the same composition chemically, but it has different textures, and because it has different textures, we actually give it a different name. So that's what I mean by say that we classify rocks on the basis, igneous rocks on the basis of texture and composition. So even if you have the same composition, if you have a different texture, we give it a different name. Case in point, basalt and gabbro. When basalt is volcanically created, it has, of course, a fine-grained texture, as you see there. By the way, I hope that you look at these pictures closely, because on the test, I'm going to give you pictures like this. I'm just going to be like, what's the texture? Tell me the texture. Here you'd say fine grained. You can't see the individual minerals. Versus a gabbro. If you gave these two rocks, let's say you ground these two rocks up into a powder, you gave the powder to a chemist and said, tell me the difference. It'd be exactly the same chemical composition, but because they have different textures, we give them different names in geology because they form differently. Okay, so this is a fine grain, okay, and that's a coarse grain. And that formed, basalt formed volcanically. Gabbro formed plutonically, intrusive rock. It formed inside the earth. Okay. All right, so let's take a look at a pie chart showing the chemical composition of different igneous rocks. Okay. Now, we actually give these kind of funny names to these different chemical compositions. And there are three important terms, four of them really, but three really important ones you need to know. Mafic, intermediate, and felsic. So mafic, intermediate, and felsic, where did these words come from? Mafic igneous rocks actually comes from a conjunction of two words, magnesium and the Latin word for iron, which is ferrum or ferric. So when you combine magnesium and ferric, magnesium and iron, you get mafic. Okay, so early geologists came up with that, coined that term, and it's stuck for years and years. Mafic, and it means heavy in magnesium and iron. Okay, you can see the silica content here is about 50%, but this mafic rocks have a lot of magnesium and a lot of iron. Okay, let's compare that to felsic. If you go to the felsic side, felsic is actually another weird word. It's a conjunction of feldspar, which is a very common mineral. It's actually the most common mineral of the crust, plus silica. Silica being, SiO2, basically. And when you combine those two words, feldspar and silica, you end up with this other word, felsic. Okay, so that's where that word comes from. And you can see that this one, compared to mafic, is richer in silica. So this one has more silica. It also has more sodium and potassium than the mafic rock. And notice that now our iron, we should see iron is orange and magnesium is olive green color. This has very little magnesium and iron. Okay? So, mafic rocks are rich, they're high in magnesium and iron. Felsic rocks are higher in sodium, potassium, and silica. Notice that aluminum is kind of interesting. It basically stays the same in all of, they're approximately the same in all three of these. Now, in between the two end members, felsic and mafic, there's another one called intermediate, right? And that's a nice term. I like intermediate because it's easy to remember, right? It's easy to remember. It's in the middle. It's intermediate between the two end members. So you'll notice that it's got a little of everything, right? It's got a little silica, it's got a little magnesium, it's got a little iron, it's got a little sodium and potassium and aluminum and calcium, okay? It's got a little of everything. So anyway, but that's the intermediate rocks, okay? Basalt is a mafic rock. I kind of want you to take a look at this because actually this is interesting to see. Basalt is your mafic rock. You see that's dark color, right? Then you have, compared to that, now these don't really, probably on the camera, they look almost the same, but this is a little bit lighter in color. This is the andesite, that's intermediate. Usually andesites are a little bit lighter in color. And then finally you get to the felsic rock, there's your granite, and you can see that this one's actually pretty, I have to kind of get the light off of it. This one's actually pretty light in color and pink. And so that's the felsic. So actually, an easy way when you're actually out in the field, and you're looking at rocks and you're trying to figure out what kind of rock you have, a really easy way is just go off of color, right? Dark black is mafic. Grayish or salt and pepper kind of color is intermediate. And then a felsic rock is usually light or light pink. Okay. So anyway, that's how you can kind of just eyeball a rock and guess its composition. So there you go. Mafic is low in silica. Okay, low in silica, high in iron and magnesium. What kind of minerals do we normally find inside of a felsic rock? We normally find pyroxene, feldspar, especially plagioclase. In fact, I'll even be more specific, a calcium-rich plagioclase. And finally, olivine. These have very low viscosity. They're more fluidic kind of melts. They can travel very far. And they create eruptions that are actually pretty gentle. These are the kind of eruptions you see on Hawaii, where you get these nice, effusive rivers of red lava that are gently sort of being erupted, and they're not making big explosions. They're not blowing up the whole island. They're just kind of gentle, effusive eruptions creating rivers of red lava. Okay. On the other hand, the other extreme, you can have felsic rocks. Okay. Now, felsic rocks are going to be high in silica. They're going to be high in sodium and high in potassium. And then we also have, sometimes they have some kind of moderate aluminum content. These are going to be, now what kind of minerals do you going to have in these? You have feldspar, a lot of feldspar. And by the way, this is in particular, this is a potassium feldspar. So there is going to be plagioclase feldspar, but it's going to be especially rich in potassium feldspar and quartz. Okay, these are very high viscosity, and these create huge, explosive, world-changing eruptions. So when felsic volcanoes erupt, these are the supervolcanoes. They're the catastrophic eruptions like Yellowstone, things that are, Mount Toba, things like this. Very, just global change when these things erupt. So anyway, that's the story on felsic eruptions. Intermediate is just like I've explained before. It's intermediate. It's between the two. What kind of minerals do you have in here? We have feldspars, okay, both potassium and plagioclase feldspars. We have some pyroxenes, but we also get amphibole. We also get some mica, okay, things like that. So these are explosive eruptions with intermediate viscosities. These are things like Mount St. Helens. They're big explosive eruptions, but they're not the world-ending catastrophic eruptions that felsic are. So again, going off of color, that's a really easy way to tell the difference between what kind of composition you're at. If you're mafic, you're going to be kind of dark, and then intermediate is going to be a little bit grayer, and felsic is going to be more pink. I don't really like this picture very much because this is supposed to be a basalt, and it looks really gray. And really, if you want basalt really looks like that. It's really to kind of get the camera off of this thing so you don't get so much glare. But it's really pretty dark black color. Now, by the way, there's another thing here I didn't talk about yet, and that's ultramafic. Okay, this is an ultramafic rock. You can see the picture up there. I'll actually show you also a real-life picture. This is ultramafic. So you'll notice that this one has a lot of a mineral that is green, and that's actually the olivine. So a lot of ultramafic rocks are green because of the olivine that's contained in them. So a mineral that you could put for minerals common in ultramafic rocks, you could put olivine. It's mostly olivine and pyroxene. Okay, so just to summarize, minerals that are common in each of these mafic rocks are mostly pyroxene and plagioclase feldspar. Intermediate rocks are mostly going to be mostly feldspar. They're almost like 90% feldspar, both potassium feldspar and plagioclase feldspar, but there's other things like mica and amphibole and pyroxene that are in them as well. Felsic rocks are going to be mostly quartz and potassium feldspar with some moderate amount of plagioclase feldspar. And finally, ultramafic rocks are going to be just olivine and pyroxene. Okay, so, and you see that all, by the way, it's all summarized down here. Whoops. Okay, it's all summarized down here for major mineral content. Okay. All right, so I've covered everything, I think. Actually, number 12. We've covered number 13. Let's look at some of these rocks and give you some more rock names, and then you can fill out number 11. Okay, so let's take a look at these. So here are the 6 rocks that you should know, igneous rocks that you should know for the test. Okay, and they're organized. Again, we have 3 compositions. We have 2 different textures. Okay, so fine-grained, coarse-grained. The different compositions are mafic, intermediate, felsic. That creates 6 different rocks, right? 6 different options. So these are the 6 you should know. First, the felsic composition. We have rhyolite is fine-grained, granite is the coarse-grained. Intermediate composition. We have andesite is the fine-grained, diorite is the coarse-grained. Okay. Finally, mafic composition. Basalt is the fine-grained, gabbro is the coarse-grained. If you want to go all the way to ultramafic, now ultramafic rocks are kind of rare. They're mostly ultramafic rocks are basically mantle. Okay, the mantle is ultramafic. If it's fine-grained, it's extremely rare. It's called komatiite. If you have a sample of komatiite, you are just really lucky. It's hard to come by. And then the more common ultramafic intrusive rock that we find sometimes is peridotite. Okay, komatiite is really only a rock that was created early in Earth's history when Earth was hotter. Okay, so anyway, I think that we've answered everything. 11, 12, we did that. 13. Now 13 is one you kind of have to think about a little bit. You know, it says if a mafic lava cools quickly, what specific rock would it most likely produce? Specific rock name from the table above. Okay, you got to kind of put 2 and 2 together with that. And that's a good example. Number 13, by the way, is a good example of the kind of questions you could have on the test. Okay, so hopefully you got to kind of combine different bits of information to come up with the answer there. We've talked about viscosity of felsic lava compared to mafic. Felsic lava is a lot more viscous than mafic lava. And we also talked about eruptive style a little bit. And by the way, the eruptive style, you either have the big kaboom that comes from intermediate and felsic, or you have the more gentle and effusive eruptions that come from the mafic lavas. Now, the reasoning for that, we'll get into that when we talk about specifically about volcanoes later in the class. So anyway, I think that we covered everything that we need to cover. I think we hit everything. So those were just reviews. So anyway, thank you for listening, and you take care. Let me know if you have any questions, and I'll see you next time we finish up igneous rocks in the next lecture. Goodbye for now.